Welcome to the fourth screencast for thermodynamics. In this screencast, we're going to look a little bit more deeply into entropy and probability. And we've already dealt with entropy a fair amount. For example, if we have a crystal of sodium chloride, which is quite organized, and it dissolves, it becomes less organized in solution. So even though the chloride ions and the sodium ions have water molecules in a reasonably orderly manner around them, it's not nearly as organized or as orderly as the arrangement of the sodium and chloride ions in a crystal of sodium chloride. So the dissolving process goes from less disordered to more disordered. That, of course, corresponds to a delta S that's positive, since the entropy increases for the system when this process, the dissolving process, takes place. And then, of course, the reverse of the ions combining to make the solid or precipitating, that has a negative delta S as the disorder decreases, going to the solid sodium chloride. Now, we've looked at this in sort of general terms, in terms of order and disorder, but let's talk about probability a little bit and how this comes into play. And for starters, let's look at a pack of playing cards. And when you first buy it, it's quite ordered. You're going to have all of the suits in numerical order: 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, Ace of one suit, followed by the same order of the next, etc. But when you use the playing cards, you shuffle them, you play games, they get out of order. And so we go from a less random to a more random structure of our set of playing cards as we use them. And that is, of course, the direction that things spontaneously will take. Now, note, this doesn't mean that we can't organize the playing cards, but that takes some effort to do the reverse process, taking all these cards and put them back into the order numerically by suits as we bought the brand new deck. That is going to take a fair amount of organizing, but if we just play around with it, what's going to happen is it's going to get much more random. So we're going from a less probable to a more probable arrangement, and that's really important to note. It's highly unlikely that just by playing with the deck, having some games, doing some shuffling, it's very unlikely we'd get this ordering of the cards. But it's highly probable that we're going to get these more sort of mixed up, if you will, orderings. And if you don't like cards, which is actually a little bit complicated to deal with, let's take a simpler example of rolling a pair of dice. Now, if you roll a pair of dice, there's a number of possible total scores you can get. You can get a 2, you can get a 3, you can get a 4, 5, 6, 7, 8, 9, 10. Anything between 2 and 12 are possible totals you can get from a roll of dice. Now, let's look at each one of these, what are called macro states. There's 11 macro states, which correspond to total score for the sum of the numbers on a pair of dice. Well, there's only one way we can get a 2. We get a 1 on both die, both of the dice. There's 2 ways we can get a 3. We get a 2 on one and a 1 on the other, or vice versa. There's 3 ways we can get a 4, a 3 and a 1, a 1 and a 3, or a 2 and a 2. There's 4 ways we can get a 5, a 4 and a 1, a 1 and a 4, a 3 and a 2, and a 2 and a 3, and so on. 5 ways to get a 6. 6 ways to get a 7, and then with 8 there's 5, 9 there's 4, 10 there's 3, 11 there's 2, and there's only one way to get a 12. We got to have 6 on both of the dice in the pair. So that gives us a total of 36 what are called microstates. So each one of these possible rolls is a microstate. There's 1 microstate for the macrostate of 2. There's 2 microstates for the macrostate of a total score of 3. 3 microstates for the score of 4. 4 microstates for the score of 5, and so on. And if we do the probabilities or the percentages on this, 2.8% of the time you'll roll a 2. 5.6% of the time you'll roll a 3. 8.3% of the time you'll roll a 4. 11.1% of the time gets you a 5. Almost 14% of the time you get a 6. And 7 is the most likely roll. There's more possible ways to make a 7 than anything else. And so 16.7% of the time you'll get a 7. And then back down in probability for 8, 9, 10, 11, and 12 respectively. So 7 is the most likely, the most probable roll of a pair of dice, and all the other combinations have lower probability. Now, okay, we've dealt with cards, we've dealt with dice. How does this apply to molecules and reactions? And again, it's kind of hard to do this with reactions, so let's do a simple physical situation. How can we have 4 identical molecules be distributed in 2 connected identical glass bulbs as shown here? So we have 2 glass bulbs, we have 4 molecules. How can they be distributed? Now they're identical molecules, but for just purposes of tracking, let's make them colored. So one's blue, one's red, one's yellow, and one's purple. And how can these molecules be arranged in these 2 glass bulbs? Well, one macro state, one possibility, is all 4 molecules are in the left-hand bulb. A second macro state is 3 molecules in the left-hand bulb and 1 in the right-hand bulb. Now notice there's 4 different ways we can do this, 4 microstates. We can have the red, yellow, and blue in the left-hand bulb and the purple in the right, or yellow, purple, and blue in the left hand and red in the right, etc. with yellow in the right, and etc. with blue in the right. 4 different ways we can do this. Now we could also have 2 of the molecules in the left-hand side and 2 in the right-hand side. And there's 6 different ways we can do this. And then 3 in the right, 1 in the left. There's 4 possible ways. And then there's only one way all 4 molecules can be in the right-hand side bulb. So we have 1, 2, 3, 4, 5 macro states. And we have a total of, count them up, 16 microstates. And it should be pretty obvious which is the most probable of the macro states. And it's clearly the one where we have 2 molecules in each side of this arrangement, 2 in the left-hand bulb and 2 in the right-hand bulb. So the most probable arrangement corresponds to the arrangement where the molecules are relatively evenly split. It's much more probable for half of them to be on the left and half on the right. It's much less probable for all of them to be on the left or all on the right, or for it to be somewhat imbalanced. Now, what happens if we do more molecules, like let's say 6? Well, there's only one way all 6 molecules are on the left, only one way all 6 molecules on the right, but there are 6 ways we can have 5 molecules on the left and 1 on the right, and same idea for the reverse. There's 15 ways to have 4 molecules in the left bulb and 2 on the right bulb, and vice versa for 2 and 4. And then there's 20 ways, the most probable, of having 3 molecules in the left-hand bulb and 3 molecules in the right-hand bulb. And if we do this now with 10 molecules or 20 molecules or 100 molecules or a million molecules, what ends up happening is the most probable distribution becomes even more and more and more likely it's the one or a few with the molecules fairly evenly distributed. So the most probable arrangements, in this case it's almost 80% of the molecules, are either 3 and 3, or arrangements I should say, are either 3 and 3, 4 and 2, or 2 and 4, and the less even distributions are much less common or much less probable. So if we go to a larger number of molecules, it's highly likely that they will distribute themselves relatively equally, about half the molecules in bulb A and about half the molecules in bulb B, that has a very, very high probability of occurring. However, if we start with the molecules evenly distributed, it's incredibly unlikely that even at some instant in time, all the molecules are on the left and none of them are on the right. And so that's a very, very low probability. And when we start getting to macroscopic amounts of substance, so we have large numbers of molecules, it's so low a probability it essentially never, ever happens. So the spontaneous thing, the thing that occurs without a continuous driving force, is in this case for the molecules to distribute themselves relatively evenly, because that's the very probable thing that will occur. And the thing that's not spontaneous to occur is the process or reaction or end result that corresponds to a very, very low probability. So it's not going to be spontaneous for two connected bulbs filled with gas to end up having all of the gas go to one of the bulbs or the other, not because it's impossible for that to happen, but because it's incredibly unlikely or improbable to happen. Now, this is way beyond the scope of this class, but it's worth noting that one can calculate entropy values. So S is equal to K log W, where W corresponds to the number of microstates and K is the Boltzmann constant. And this is in fact the famous equation that is on the grave of Ludwig Boltzmann, who was instrumental in sort of determining how this sort of thing works. This is called statistical mechanics, the study of this, and it involves dealing with probabilities and microstate arrangements. And again, way beyond the scope of this class, but hopefully that gives a little bit of a taste for how spontaneity, entropy, and probability tie together. And that is it for the fourth and last screencast for this unit.